Okay, guys, so today we'll be talking about GaussDB. It's it's a cloud native multi-primary database with three levels of disaggregation: compute, memory, and storage. So what's the problem statement? So not having multiple writer support leads to limited write throughput and also limited scalability. So existing cloud databases have properties of high elasticity, high availability, and low cost. This was mentioned in the paper, but I don't know how much less does it cost. So examples are Aurora, AlloyDB, SQLDB, Taurus, PolarDB. Existing architectures mostly have primary standby model where you have a single primary that writes and you have multiple standbys where from where you can read. So like for example, Aurora, it has optimistic concurrency control to detect write conflicts, but then it suffers from high abort rates and lower performance. If we talk about Taurus, it has pessimistic concurrency control for cache coherency, but then it suffers from high concurrency control overhead. So PolarDB has a stateful memory layer. So now the compute node has to interact with memory layer for its transaction processing. So this leads to inefficient recovery of memory layer. So generally, if we see multi-primary architectures can be divided into two parallels. One is shared nothing and the other is shared storage. So if we talk about shared nothing, we already know a lot of examples are there: Spanner, Cockroach DB, TIDB. So what happens? What's the fundamental design principle? It's like physically partitioning data into different shards. And if you have a transaction in a single shard, you will use locking. And if you have a transaction across shard, they generally use two-phase commit protocols. So what they suffer from? They suffer from low performance, high latency for cross shard transactions. And also they have to deal with the complexities of sharding, like on what to shard and stuff like that. And not all workload would be sharded in a proportionate manner. So if we talk about shared storage, you have Oracle RAC, IBM DB2 Pure Scale. These are the examples. They logically partition pages onto different writers, and they rely on conflict detection and cache coherence mechanisms. So GaussDB is a shared storage architecture with more things, more design principles. One of their top level design principle is of disaggregation. So they have a notion of three-layer disaggregation. So compute, memory, and storage. And obviously, when you have this form of disaggregation, the primary benefit that you get is elasticity. You can scale up and scale down individual nodes as per your requirement. So let's talk about compute. So compute owns a subset of pages. These are logically partitioned. It does the SQL optimization and execution. It runs the transaction management system, and it also orchestrates the recovery. What does memory do? Memory is a stateless. It maintains a global state of page ownership directory because now nodes or the compute nodes own the pages for running the transactions on them. It also has a global buffer manager and a global lock manager. Storage. So storage keeps log persistence, page persistence, and it also helps in recovery. By the way, they also have memory to help with the recovery as well. So this is the design, that diagram that was there in the paper. So we have compute, we have memory, we have storage. Compute has this SQL optimizer, and it also has a local buffer manager, local lock manager. It runs the two-tier recovery manager. It also has small component of training of smart routing manager. Then the memory has page owner directory management, global lock, global buffer. It also has memory checkpoints. So the storage has your recovery logs, redo and the undo logs segments. It also has checkpoints, and it also keeps the data in the pages. So let's get into more details of each one of these. Compute layer details logically and dynamically assigns page ownership to the nodes. Why is this needed? It's needed to generally most of the time avoid conflicts. So SQL optimization, execution, transaction, it handles. So the way it does this is it first acquires the page ownership, then only it can modify. This is how it supports multiple writers. So any nodes, any compute nodes you can write through, but then you have to acquire page ownership and then proceed. And write changes are written to the redo log stream. Every compute node has a redo log of its own. This is to uh, streamline the recovery, and only one owner has write privileges. Non-owner nodes are allowed to get read-write privileges to access a page, but then if it's a write privilege, they will transition to the and become the owner node. Compute layer also has local buffer manager for the pages it owns and local lock manager for accessing those pages and tuples. So node owns all relevant pages, and if a node owns all the relevant pages, the transactions can proceed locally, work with the local buffers, with the local locks. If not, then the way it works is you have to find all the pages that are part of that transaction from the page ownership directory, acquire the ownership of these pages, and then you can proceed with your transaction. So val manager, write-ahead logging manager, and an undo segment manager is also there in the compute, and this is there to maintain the A and D of the asset properties. Individual, we discussed that, and so the redo log stream is individual per compute node, and it's primarily for performance to avoid expensive synchronization across compute nodes, and also to avoid significant filtering of irrelevant logs if it was a shared one during node recovery. So shared undo segments, but it has a shared undo segments for all the compute nodes. It has a two-tier recovery manager, memory checkpoint manager, and storage checkpoint manager. It also has a query routing layer, which so generally the scene is that pages have data affinity. So if you randomly assign pages to owner nodes, it's an in or queries to different owner nodes, it would be inefficient because you would not know which pages are owned by which particular node. So we want to optimize and route the query to a node wherein we know that most of the pages that node owns. So page frequently co-access should have the same owner, and this is where the smart query manager has some logic of getting to know and routing these queries to those nodes. So let's talk about the memory layer. So memory layer maintains page ownership information. Now, what happens is that to maintain page ownership of all the pages is very expensive. So you maintain ownership of only those pages that are there in the memory. And for the pages which are not there in the memory, when they are loaded from the storage, that's when you assign the ownership for those pages. And this is shared, and this is global, and all compute nodes can access it. But then this leads to further problems because it can be huge, it can still be huge. Then you have to distribute it across all the memory nodes, and they use consistent hashing for that. So every local pod on a memory layer maintains a subset of page owners. The same properties applies to global lock management also. That is also maintained at the memory layer, and it's also spread out across using consistent hashing. So yeah, uh, storage layer. So page and log persistence is there. We saw individual log stream is also kept. Storage checkpoint is there. Shared undo segment is there. That also maintains all versions of MVCC updates. And the segments are partitioned into fine grain blocks, wherein what happens when a transaction runs, it asks for a block via global lock manager, which maintains older versions in this block. And when a transaction completes, then it releases the lock, and blocks can be used by the other transactions. So what does the paper claim? Paper claims that they were able to achieve higher transaction throughput, lower latency because they ran into fewer aborts compared to the other storage layer log transaction conflict detection. They were able to recover fast because of their two-tier architecture augmented with checkpointing at both the memory and the storage layer. They were better at scale out and scale in ability because of three-layer disaggregation. And because of the smart placement method, they were able to capture data affinity and route the queries to the appropriate compute nodes for lesser conflicts and movements of page ownership. So now let's get into how a transaction is processed. So transaction is routed through a compute node to a compute node, and as mentioned earlier, you have to get the ownership of all the relevant pages. And then it uses two-phase locking to lock the corresponding tuples inside a page. Execution of a transaction on this node, then it can see that the page can be on any of the nodes. Now you have three types of nodes. So if a compute node, if the page is on the compute node, then that compute node is the page owner. If the page is on the memory node, it also has a page owner. But if the page is on the storage node, it doesn't have a owner yet. So each page in compute or memory node generally keeps some information, and that is like, this page is owned by which node? Is this page only a read only cached page to accelerate reads, or is it a page that they have a notion of past image that is also used to accelerate recovery? We'll probably see briefly in future slides. So the way is that to find a page, you have to look in the local buffer pool. If not, you go to the page owner directory to locate the owner. Page owner directory is on one of the memory nodes. So the page owner directory pod structure is like, you have a page ID, then you have an owner node ID, you have a lock information, which nodes lock this page, what nodes are waiting for this lock. Similarly, you have global lock structure that also has object or table locking to current node that is logged, locking transaction ID and locking privileges. You also have a waiting queue for all waiting transactions on this object, etc. So we'll just go over page write. There is page read also, probably will not go, but I've added in the slide. We can refer later. So how does a page write work? So you check the local buffer pool, whether the owner is, whether it's the owner, if the node is itself is the owner of the page and the page is in the local buffer pool, you get the write lock from the local lock manager and you can proceed with the write to that page. But if the node is not the owner, then page may not be in the local buffer pool, or page is in the local buffer pool but the node is not the owner. So get corresponding pod entry from the memory node, and what can happen? The page entry may be in the pod or may not be in the pod. So if it is in the pod, get ownership from the memory node or any other compute node who can be the owner of this page. So if a memory node is the owner, you get the ownership via the pod. You move page from memory node to the local buffer pool of this compute node. You set itself as the page owner. If you cannot get the page ownership, you have to wait until you get access privileges. So if the page is in the other compute node, then you have to get the ownership from the other compute node via pod, and then you have to move the page from the other compute node to your local buffer pool. Then you set yourself as the page owner. If you cannot, then you still have to wait for the lock. But if the page was not there in the pod, or it was not there in the other compute node as well, so then the page is there on the storage node. So you load the page in the storage node, and then you are the owner of that page, and then you proceed as per earlier. Now you have access. I'm not going into read for now. So we'll talk about some optimizations as part of transaction processing. They have a read authorization optimization. It improves read performance. What happens is that you can still keep the page in the non-page owners who are frequently accessing a page only for a read. It would not be the owner of the page, but it will get the read privilege. The ownership still is with some other node, or maybe with some other node, and when that node updates the page, it will invalidate all of these read authorizations. So this information also has to be kept in the pod. That's the common place where all the nodes can refer to. So we'll briefly talk about two-layer locking. So you have a local lock at each compute node. You have a global lock at the memory layer. Now the page owner has to get the local lock. You don't need global lock if you are the page owner. But if you're not the page owner, you need to get both global lock and the local lock. And the way you do it is, you first check the global lock that is there at the memory node. If the page was not logged in the global lock, you need to check local lock of the corresponding node owner. And if the page was not logged by the local lock of the page owner, node gets the lock, otherwise waits for the lock. So this may sound confusing, but the general gist is that you cannot work with a page until you have the lock. You may yourself be the page owner, so you can get away by having the local lock. If you are not the page owner, there is some other node who is the page owner. Now you have to move the ownership from that node to yourself. So you'll have to take global lock and the local lock of that node, because since that node had the page ownership, it might have locked that page locally and would have been writing something on that page. So you'll have to wait for that time until that write is done to get the ownership, and then the transfer happens. So regarding the past image, so what happens is that, suppose if a page ownership is moved from node N1 to node N2, you can still keep the content of the page in N1. Why do you need to do that? And this fastens the recovery. So but you keep the content in N1, you cannot make it still, you cannot make N1 still the owner. So you mark this page that with some meta information, which these people call as page past image. So when N2 fails, the new node fails, you can still recover with the page information that is there in N1. You don't need to go to the log recovery. So this fastens the recovery. So now with this, now let's get to the recovery part of this. So recovery, what happens is that, how do you do a pod recovery, which is there at the memory node? So pod records ownership of each page we have seen. if the memory node fails, the pod is lost. So you need, but you can because the memory node is stateless and every compute node has ownership of its own page, you can reconstruct the pod by scanning all the compute nodes. So compute node has this information, then you can scan. If the compute node fails, then you can scan the pod to get the pages owned by that node, because the pod also has that information. But if both the compute node and the pod fails, then you can reconstruct pod while you are accessing the pages from the storage node, and that's where the ownership again will get assigned. If you How do you recover the global lock recovery that is there at the mem node? Because the reconstruction, so you reconstruct by scanning the local locks of the compute node. So generally, if you want to recover things at memory node, because it is stateless and the state is maintained at compute node, you get the state from the compute node. But if the compute node is also down, then the final source of truth is the storage node, but now that doesn't have ownership details. So as and when, as the form of querying, you want an access to a write access to a page, that's when the ownership would be given when you're reading from the storage node. So how the page recovery at the memory node happens? As the memory node is stateless, no recovery is happening, and the pages are also present in the storage node, so we are fine. How does a lock recovery happen on the compute node? If the local lock is down and the lock is present in the global lock manager, which is there at the memory node. So same logic. If the local is down, go to the shared or the global lock manager, get the information from there. If the lock is absent from there, you were the owner, so you just restart yourself, and the local lock anyways is lost, information is lost because it was not there in the global also, so you cannot get it from there. And when you restart the operation and proceed again with the requesting the lock, it will be a fresh lock and you will reapply the locking as per your part of the query processing. So how do you recover from page recovery at the compute node? So when a compute node fails, it needs to recover the pages in the compute node. So first select a new compute node, fetch the log and do the log recovery. So you have undo redo logs to achieve failure recovery, and you also have checkpointing done at the memory and the storage layer. So you try to recover from the memory checkpoint first because it's faster, but if you cannot, then the ultimate source of recovery would be to use the storage checkpoint along with the logs that are stored on the storage layer. So how do you do? So tidbits about redo logging. So what happens is that, as we discussed earlier, that every compute node has an individual redo logging scheme where each operation to the page is recorded, and the log is also assigned a log sequence number. But because your page ownership can move between nodes, right? Page can have an update from different nodes, and then you have to recover transactions for that particular page, which can be spanned across those nodes. So there is a need of some kind of order, sequential order, that needs to be followed for this recovery, which has a distributedness in nature. So how do you do that? So to have this partial order, they make use of Lamport clocks, and when a page ownership moves from B to A, they set the log sequence number as max of account bigger than the previous one and what's available at the local one. So that's how you have that relative ordering for replaying when you are trying to recover. So undo segment is like all the active and the incomplete transactions are scanned from the undo segment, and it applies the transaction from end to begin. It also has track, it also keeps multiple versions to support MVCC. There is a lot of more detail about these things in the paper. It's pretty much very complex. I have a lot of slides at the end of this which gets into more details, but we'll not be talking more about it though. So this brings us to the smart query routing. So what happens is that it makes use of JDBC ODBC layer to route the query to the appropriate compute node. Why it wants to do that? Because are if you're making this call at the compute node and you figure out that this node itself is not the right node, then you have to retransmit to another relevant node. So to avoid that, they do it at the JDBC ODBC layer. And the way the smart routing works is they make use of graph partitioning for that. How they do is that each vertex is mapped to a page. Edges between the page determine their frequency of co-accessed, like are they being accessed together frequently by multiple queries. If yes, their weight increase. And then you have graph partitioning algorithms to partition these graphs into subgraphs, where each subgraph can be owned by some owner node, and that node will process these queries to have maximum, to avoid the conflicts. But now the problem is that it is expensive to build a page graph. So you have to group multiple pages into a single node based on keys, and then you periodically update the graph and graph partitions. But then what is the another issue? The another issue is that it is expensive to obtain all the pages that are being accessed by a query. So then if that is the case, then these guys make use of multi-layer perceptron to predict the accessibility. And the way they do it is that they have a query encoding and as the input, and the output is the access vector, where each element denotes the access possibility of a page group. Each element is a page group, and then you have nodes with the ownership of page groups, and then you do a similarity search on this to route the query to the node that has the maximum similarity with the access vector. So the workflow is that you have a light query routing model at JDBC ODBC layer, and then you compute. The compute node processes the query. It asynchronously sends the query an access vector to a model to fine tune. When this fine tuning happens, it updates its routing model as well, and then the server will periodically update the inference model that is happening at the JDBC and ODBC layer. So let's talk about the performance. I've not added all the metric details and everything, but I've just collected a gist of what they meant by performance evaluation. So they say that GaussDB is better in terms of throughput latency on TPCC as well as Sysbench compared to SystemX, which is a shared model, and CockroachDB, which is a non-shared model. So why they were better to a shared model is because SystemX suffers from a lot of page movements and recovery from storage nodes. So it doesn't have a smart query routing. So a lot of page movement is happening even if it is shared, and the recovery runs through storage nodes. So they don't use two-tier architecture. And compared to CockroachDB, the main point is that the cross node communication, because it is shared nothing, the cross node communication happens with two-phase commit protocol, and they say that that is expensive. So yeah, because of smart query routing, they have less page ownership movements and they have faster recovery. So this is their claim, that these design principles were able to get them better performance compared to these two systems. So what are my views on this? I feel that the scalability tests that they did were just 6 nodes, maxed out to 6 nodes, which may not be a good scale limit number, I feel. And my intuition about this whole approach is that shared nothing might be better suited if we want to see much more scale for nodes, like maybe 20, 30, 40, I don't know. Because when that would happen, I feel that this approach may result into a lot of movement, even with the smart query routing. But I really like the smart query idea, and also their split of training given to their compute nodes and inference moving to the JDBC layer. But with these disaggregated layers, I think the recovery, though it may be fast, it seems complex to me. But that's true with any complex systems. So yeah, I'm done with my presentation.